Okay, now let's start with something that is actually interesting. Let's do a loop. And the reason we are doing a loop is we are going to be trying to deal with two things. We are going to be dealing with loops themselves, and also we want to be able to understand how branching works. Because as it is, you need some way of directing the program flow, and the way that we usually do it is by using loops and by using conditions, and those conditions usually mean that we are going to be doing some sort of declaring a condition and then doing conditional branching based on whatever the result is. So what I want to do, I basically want to count from 0 to 512 in order to show some things. So first thing first, let's create start the program, and let's create a label, and let's say call this a main, and let's just say that I'm going to move to R0. I'm going to just move the value of 0. So I'm basically just resetting the register to make sure that the 0 is there. It should be already reset to 0, but I need to make sure. Now let's create a loop. Loop is going to do this. First, I'm going to see, have I reached the value that I was intending to. So I'm comparing R0 to 512. All values are decimal. In order to be more consistent, I'm going to say that I'm comparing 512 to R0 because I want to try to always read from the right to the left. So let's say we are comparing 512 to R0. Now let's do conditional jump. So branch if equal, and we are going to be branching to somewhere down there. That is going to be end. Let's call this end, wherever end is. We don't need to do this. We can also just say end, because end is implicit. But what we can do is we can call it specifically. I'm going to reset it just to see how this thing is going to work. So I'm just going to leave it here, like this. Now let's add 1 to R0. So R0, 1, or 1. And now let's go back to the loop. So the idea is pretty simple. We set R0 to 0. We compare it to 512. If the comparison is equal, so if those numbers are equal, we jump to the end. If the comparison fails, we're just going to add 1 to R0 and then unconditionally go to loop. This should work. Also, let's just quickly create a stop, and let's do unconditional jump to stop, so that once we have reached the end, we can simply go outside of the loop, and that's it. Now let's first compile and run this thing as it is. I'm going to go and step into it just to show how this thing works, and then I'm going to run it. So now let's step into it. My program counter has changed. My R0 is 0, so I'm going to compare this to 512. I'm going to see, okay, that's it, I don't care. I'm going to go and step into it. I'm going to add 1 to R0, and this is going to be the loop that I'm going to be moving through basically forever. And then after a while, I'm just going to continue. and after a while I'm going to end up somewhere. Let's now go and see what happened. Let's now go and go back to my memory and see what actually happened there. First, let's jump to the address of 0000 and start the memory. Let's analyze what happened to the registers first. My program ran completely okay. Everything was fine. I went to 512. This is the 512 written in hexadecimal, so this is fine. The reason why the rest of it isn't fine is because the once I got to the last or the part of the loop that was just before the jump, or when I got to the jump, I jumped to the end, and end is here. Now, what happened is that the memory is filled with values of A. And this is just simply how the memory is filled in this simulator. What happened is that when I jumped to the end, and I didn't specifically denote where the end is, the program itself decided that, or the simulator decided, that the end is going to be the end of the program, simply because we have a start, then we have the end. Underscore end is something that is implicitly defined by the assembly. Now, the thing is that once this thing said it's going to jump to the end got assigned an address. So this address is 18 hexadecimal. And the reason for this is because the assembly needs to know where to jump. So once I reached the number that I was aiming for, so 512, this became true. I jumped to the value of 18. I executed branch if greater than equal this, and this jumped to some location in the memory. That was it. So the problem that I have is that this is working kind of okay, but the thing that it's not doing is not doing it correctly. It is jumping to the end, and since end is not defined, I have absolutely no idea how to end the loop correctly. So what I'm going to do, I'm going to fix this one. I'm going to say, okay, I'm not going to jump to the implicit end because the implicit end is there. I'm going to jump to stop. This way, once I go through the loop, and once I reach 512, what is going to happen is I'm going to be jumping to this stop, and then this is going to just branch in the infinity loop. Let's just try this thing over. Let's restart and let's reload. And now let's step into. So I have reset R0. I'm going to go 1, 2, and so on. Let's continue. And now this is much better. I have reached the value of 200, so 512 decimal. Now I have reached this position here, so the address 14, and I'm in a continuous loop because this thing is running. So I did what I wanted to do. Now let's pay a little bit of attention how these things work. The branching itself is simple. You just have a bunch of different conditions that you use as a postfix for B. So B equal BLT, BGT, and so on, less than, greater than, and so on. If the condition is true, it is going to jump to the label that you provided. If the condition is not true, it's just going to continue straight on. This is unconditional looping, so this can loop to wherever. So what I'm doing is I'm in an unconditional loop here, and I'm seeing, do I need to jump out of it? And then I have another unconditional loop down there. So this is pretty straightforward way of doing this. Okay, let's do something different now. Let's talk about how do we control something that is outside of our processor, or let's call it periphery, or input-out devices, or however. What I'm going to be dealing with is I'm going to be talking to these LEDs here. These LEDs here are, I can show them either as 10 of them, or I can show the entire 4 bytes of them. So there is 32 LEDs that are assigned to the location that is pointed to by this number here. So basically FF200,000, or part of the memory. And this part of the memory, if I write to it, I'm going to be setting these LEDs on depending on the value that I write to it. I'm going to be simply using the value of 1 at the start, and then I'm going to be dealing with different values to show you how these LEDs look like. And also later we are going to be doing a counter. So we are going to be just moving the LEDs and counting by 1 while we are at it. Now, there are a couple of ways of doing it, but I'm going to be faced with the problem. What I would do normally is I would load the information about the LEDs directly. I would probably use something like, let me just start with the wrong command. So I would just do a store, and let's say I would just do a store and say I want to store the value of I don't know, whatever. Let's define a value. We are going to use R2, and we are going to say that we are going to be defining the value of 0B12341231. So this is the binary number 1. It makes no sense to write it like this, but I want to just keep it as a whole byte so I can just show you which LEDs we are going to be turning on. So I just put the value of 1 to the register R2, and now what I would do if I didn't know how to do it, I would say, okay, store R2 to the location of FF2 to then 1, 2, 3, 4. So this would be the way that I would do it if I didn't know how addressing worked. Now let's try to simply compile this. If I compile this, I'm going to get an assembler error, and this assembler error is going to be internal location not fixed up, offset not fixed up. Why is this happening? The reason is simple. When I'm encoding instructions, I only have 4 bytes. So I cannot directly encode a value that takes 4 bytes inside one instruction, and this would require this instruction to be the opcode, and the value itself would have to be in those 4 bytes. So there is not enough space for what I was trying to do here. So how do I solve this? Usually, and the simplest way to do it is to define something called a data block, and say this. I'm going to say this is the data block. Then I'm going to say we are going to be calling this data LED, and then I'm going to be just putting the data here. So this is the value that I was trying to deal with, and also I'm going to be prefixing it with 0xFF. So this is the hexadecimal value. Now, what does this mean? This means that I have stored, or I have told the assembly to store this information somewhere. It's going to allocate a part of the memory, and it's just going to store these 4 bytes, and then it's going to give them a name. It's going to be called LED. Now, I'm going to be using this location in such a way that I'm going to be saying I want to load the location that I'm going to use into register R0. Now I can do this. If I do the equal sign and then say just LED, it is going to recall the information from the location, and then it's going to load this into R0. Now I have achieved what I wanted. I wanted to store the information that I encoded in the particular place in the memory into the register so I can use it later. Now, the rest is pretty simple. If I want to store whatever is in R2, I need to reference the value, so I need to reference the memory, and the way to do it is to use the brackets. So I'm going to be using square brackets, and the square brackets is going to be just referencing from R0. So I'm telling it now, take whatever is in the R2 and stick this to the location that is pointed to by R0. So this should be doing the right thing. So this should be turning the LED at the location 1 on. Now, let's say, okay, I want to create a loop. I'm going to be creating a loop. Let's call it right. And now I'm going to say, okay, now I have right, and then I'm going to be jumping to right because I want to be able to be in a loop. Now that's it basically. If I compile this, it should compile, and now I can step into it, and I'm going to see how this is working. So first, it jumped over the first one, so jumped to the first one, sorry, and then it checked. Okay, it was storing the R2 with the value of 1. This was done. Then it says load R0 with program counter plus 4. This is because when I assigned my values to the LED label, it told the assembly that it needs to allocate some sort of memory, some part of the memory, and put the value that I was inputting into it to the I wanted this value to be put inside the memory. So this location in the memory is not holding the instruction. This location in the memory is actually holding the data. So this is considered data. This is not SVC something. This is just data being encoded in the memory. Now I'm going to be recalling this information to the R0, and you're going to be seeing that R0 is now FF2 and 5 zeros. Now the next thing is write. I'm going to store, and what happened here is that the last LED became 1, and now if I continue, this is going to be just spinning in an endless loop. This is going to be it. Now let's stop this. Let's create a change. Now I want to delete my or reset my LED. How do I do this? I can just say store the value that is going to be changed. Now what I'm going to do is I'm going to just move R2, and I'm going to put the value of 0 into it. I don't care which 0 it is, because this 0 is going to be the 0 of it's going to be 0. Binary 0 is the same as decimal 0 is the same as hexadecimal 0. So I'm going to be storing R2, and I'm going to be storing at the location pointed to bar R0. So now if I compile this and if I continue this, you are going to be seeing that something is happening here. But what you don't see, if I stop it, I can step into it. What you're seeing is that I have turned off the LED, because my first pass was good, but my second pass wasn't. So what happened is that I was storing R2, the location of R0, but I didn't do the move. So I'm going to put this move inside my loop. Now I'm setting the value for the LED to 1. I'm storing it. Setting it to 0, I'm storing it and looping. Let's compile it. Let's continue it. Now I can see this LED blinking. This blinking is completely off. By off, I mean it seems like it's blinking, but it's not blinking in any with any normal delay or with any regularity. The reason why this is happening is because the rendering engine that is rendering the LED here is much slower than the pace that we are turning our LED on and off. So what I'm going to do is I'm going to introduce a delay. The only reason for this delay is because I want to see my LED blinking. The way I'm going to introduce a delay is I'm going to just count to some number, and then once I get to this number, I'm going to be getting out of this. So let's introduce a delay. This delay is going to be called delay. And let's say that I want to do it this way. I'm going to be before I do a write, after I do the write, I'm going to be storing I'm not going to be storing, I'm going to be moving the value. Let's say move, I'm going to be using some register, let's say R5, and I'm going to be putting 0 into it. Then in my delay function, I'm going to be adding or I'm going to be comparing it to a large number. Let's say I'm going to compare R5 to let's use this number. This number is something that is going to work because it is able to store this number in my instruction, or in the space selected for the instruction. So I'm going to compare this R5 to this number, and then I'm going to say now if this thing is not equal, I'm going to be jumping to underscore delay, and if they are equal, so if they are not equal, I'm going to be jumping to delay. If they are equal, this is not going to happen, so this is not going to go then. What I also need to do, I need to add 1 after before I compare, because I need to increase my the value that I have by 1. So this should be it. And now I'm going to be moving the my LED to 0, and then it's going to be reset to 1. Now the problem that I have is that I'm setting my LED to 1. I'm waiting for a certain amount of time, 102,000 cycles, and then I'm setting it to 0, and then immediately setting it to 1. So I need another delay. I'm just going to copy this thing, and I'm going to be saying, okay, after I have reset my I have reset my LEDs, I'm going to redo the thing. So I'm going to be first moving the information, or I also need to reset this thing. So I need to reset my R5, and I need to reset it and use 0. And then I'm going to be adding, I'm going to be comparing, and then I'm going to be going to delay 2. And then after the second delay, I'm going to be going back up. So if this works okay, let's see. I'm writing the 1 to my R2. I'm storing R2 to location pointed to R1, R0, and this means that I'm going to be turning on the LED. I'm resetting my R5. Now I'm doing a small loop, and this small loop is going to be a loop that is going to be counting to 102,000 by 1 and delaying. After it has done this, I'm going to be moving R2 with the value of 0. So by doing so and storing it, I'm going to be resetting the LED to 0. Then I'm going to start my loop again. So my loop is going to be the next loop, and this next loop is also going to count to the value of 102,000. And then I'm going to go back up, and I'm going to just go straight back to the loop. Now let's compile this thing. And if everything is okay, my LED should be blinking. This is still too fast, but now it sort of makes sense. Okay, this now works. It's not beautiful. It's sort of kind of kludgy, but it works. Let's do another thing with these LEDs. In the previous example, I was just lighting up and turning off, so turn on and off the LED, the last LED or the first LED, however you count it. Now let's try to animate something. What I'm going to do is I'm going to be creating an animation in such a way that I want to just add one to the location of the LED each time this loop is completed. What I need to do this is I need to first move the LED outside, or move the first assignment of the value to the outside of the loop. I need to add R2, and then 1 before lighting up the LED, so that I light the red correctly my LED. And then what I need to do is, when I'm turning off the LED, I need to make sure that I'm turning off the LED not by using R2, because I cannot reset it inside my loop. I need to use another register, so I'm going to be using R3, for example. And then I'm going to be storing R3 to the location R0, meaning I'm going to be just resetting the LED. So this means I'm going to be lighting up some LED here. This number is going to increase every loop. Then when I go through my delay, after that I'm going to be just writing 0 to the LED to turn off all the LEDs. And then I'm going to be going through the second loop while the LEDs are off, and then I'm going to be writing from the start, and I'm just going to be going back to the beginning of the loop. Now let's compile and see what I did. What I did is I actually created LEDs that are blinking and adding to 1. Now this isn't too helpful. The reason why this isn't too helpful is because I have a lot of delay, and since the speed at which everything is running makes everything continuously blink, it's like it almost makes no sense to have this part of the application, or this part of the assembly running. I can simply just, without resetting the LEDs, I can just say, okay, I'm going to move this one, and let's start see what is going to happen. Let's continue. Now it's moving much faster, and also it's not blinking because I'm not resetting the LEDs, since it makes no reason to do it since I'm counting. Okay, now let's stop and let's do another thing. Instead of adding, so right now here I'm adding R2. Let's try and do something else. Let's do another function, and this function is not going to be adding. I'm not going to add 1. What I'm going to do is I'm going to be rotating right. So I'm going to be doing this. I need to rotate by 1, and also I need to set a bit, because I need to set a bit in order to be able to rotate. So I'm starting with 1, and then I'm going to be rotating right and moving through the LEDs. Let's see what is going to happen if I compile. Let's try to continue. And now I actually managed to show how rotation works in the 32-bit values that I'm using as a reference. Also note that this is so quick that I'm actually doing 2 delays. I'm rotating, showing the LED, creating a delay, then creating another delay, and then I'm stepping up, and it still rotates extremely quickly. If I remove all the delays, you probably wouldn't be able to notice. It would just blink completely randomly. based on how quickly the thing is able to do. The last thing I did was the delay and the rotate to the right. Now let's do one more example, and this example is going to be a little bit different. What I'm going to be doing, I'm going to be modifying my code in such a way that I'm going to be talking to the switches, and I'm going to be using the switches in order to influence the LEDs. The idea is to basically just map the memory, or just to clone the memory from the location that the switches use to the location that the LEDs use. So if I click the switch here, the particular LED that is stored in the equivalent of the switch just turns on. How do I do this? First, I'm going to be needing to define the location of the switches. The reason why I need to do this is the same as with the LEDs. So I'm going to call this the SW, and I'm going to say 0x FF, and then 2, and then 1, 2, 3, then 40. Now I know where the switches are. The next thing that is going to happen is that I'm going to be using the register, let's call it R1, and I'm going to be using this register in order to hold the location of my switches. So I'm going to be storing the value of SW to my R1 register. I don't need the register R2. The reason why I don't need the register R2 is that right now I have no use of trying to use another register for any reason or the other, because I have the switches, I can read from them, I have the location of the LEDs, I can use those. So basically what I need to do is I need to read the switches, and then I need to be able to store the information that was on the switches into the LEDs. So how do I do this? The simple example of this would be doing this. I don't need this row here. So what can I do? I can first read, so I'm going to be reading the value of the switches into the register, and I'm going to say, okay, read whatever is R1 is pointing to, read it to the R2, and then store the information from the information that is in R2 to the location is pointing that the R0 is pointing to, and then loop. If everything is okay, if I compile this thing, and if I continue it, once I push the switch, I turn on the LED. If I reset the switches, let's turn off. I can turn on all the LEDs and so on. So I'm doing a simple thing. I am referencing memory, reading from the memory, and then directly writing to the next location. That's it. I'm mirroring. This is going quite quickly. I'm basically managing to do something like 19 million instructions per second. And this is extremely quickly when it comes to a simulated processor. Okay, this has been the part where we were doing the examples of control and the simple control when it comes to communicating with the LEDs and communicating with outside devices. What is left is to try to do different things and try to understand how the 7-segment displays work. This is something that is going to happen in the next episode. Thank you for being with us, and see you next time.